All right. Today we will continue with our discussion regarding block diagrams. We have seen the block diagram corresponding to discrete time systems, and the discrete time systems were indicated by this delay element. We were using a delay element which makes a delay, as you can see. X of n is the input and x of n minus 1 is the output. In the future, when we see the so-called Z transform, which is related to the spectral characteristics, the frequency characteristics of, of a discrete time signal or a discrete time system, we are going to use a notation like this. Or if you search from the internet, you will occasionally see that the notation that can be used instead of this D as a delay element would be this Z to the minus 1, which is again a delay element. So in a sense, you shouldn't be confused about the notations that you encounter. And in the systems corresponding to continuous time differential equations, now we are going to need derivatives and integrals, either of them. So you may think of the situation like x of t goes into a system that takes the derivative. So it's a d by dt system, let's say. And the output is therefore x prime of t, which is d by dt of x of t. If you have seen differential equations, you may remember a Laplace parameter that is that could also be used in this format. So you may notice that in some cases, people prefer to use S here, which would again produce x prime of t. If you remember that parameter of S when you were solving differential equations. This is coincidentally also a frequency related or a spectrum related parameter, and we will also see that. We will see the Laplace transform. So Laplace transform is also useful in that aspect. It will take the time derivative. And an alternative way of putting these things is the following. X of t goes into a system which is actually an integrator. Let me put an integral sign over there as if I'm integrating the input. And the output is x sub, let me look at my notation. Do I put it in a parentheses? Yes, in a parenthesis, x sub 1 of t, which means the first integral, excuse me, not derivative, the first integral of x of t, which could be notated as from minus infinity to t x of tau d tau. This is the integral of x of t. And it is also equal to x of t convolution with u of t, because when you convolve anything with u of t, it actually corresponds to the integration. And we are going to use this one, by the way. This is the notation that we are going to use to describe differential equations in continuous time. So we won't be using the derivative notation, but we will be using the integral notation. In terms of the Laplace parameter, the S parameter, the integration could be notated as x of t going into S inverse or 1 over S, giving you x sub 1 of t, the integral of x of t. So this is the building block that we will use. You can either type s to the minus 1 or type an integral. We haven't seen the Laplace transform yet, but you know differential equations that that's why I'm telling you that you could use that. But for us, the notation is just a tall integration symbol. It's like the clef symbol, as we know, the tall clef symbol. So how are we going to use this? We are going to use it for describing, or for first by converting the differential equation into an integral equation format. And that confuses things because the ordering of the signals will change. The signal itself will be like the most integrated. The first integrated will also be integrated, the first derivative. Let me write it. A times x of t, for example. Let me say a1 x of t. Or shall I start from the output? I will start from the output side. A1 y of t plus, no, a0 y of t plus a1 y prime of t plus a2 y double prime of t plus blah blah is equal to b0 x of t plus b1 x prime of t. By putting prime, I mean the first derivative. The double prime is the second derivative, etc. b2 x double prime of t plus etc. Suppose that those etc. goes, they all go to a level of, or a number, the derivation number of, let's say, n, capital N. So the last term here is a sub n y prime, double, it's not double prime, but it's the nth derivative that we have. And at the right-hand side, it's again the nth derivative. So how do we convert all these things to an integral equation? For that, we need to integrate n times. And every integration can be considered as a further convolution with u of t. We convolve with u of t again, and then we convolve with u of t again. That corresponds to iterated integration. If you want to write it in an iterated integration format using the integral symbol, like from minus infinity to t x of tau d tau, the expressions will get more and more complicated. Look at even one further integration, which would correspond to x sub 2 of t, for instance, would be equal to, from minus infinity to t, and the other one, inside it, I will have from minus infinity to tau, and inside it, I will have x of some different terminology, let's say x of sigma, d sigma. This is the second integral, because inside this one will give me, and then d tau, of course. The inner side of the integral expression will give me x of tau, and out of that will be integral x tau d tau, which will give me x of t. So soon we will run out of terminology, the indexes, tau, sigma, the Greek letters will end. So it's difficult. Instead of that, we just say it like x sub 2 of t, which means a double integral form, or twice convolved with u of t. So we will just take the nth integral of both sides of the long equation that we have now, which will convert everything to a0 y sub n of t plus a1 y sub n minus 1 t. Why do I put n minus 1? Because I integrate n times, but I integrate n times this term, which is already a derivative. So one derivative and n integral will give me n minus 1 integral in net. So, and then we will continue like a2 y n minus 2 t, blah, blah, all the way up to a sub n y of t. originally the last term was the nth derivative, and I integrate the nth derivative n times, and I come up with y of t. And this will be equal to the right-hand side, it looks the same. B0 x sub n of t plus B1 x sub n minus 1 t plus etc. all the way up to b, excuse me, b sub n x of t. So the orders of a and b, like from a0 to an, and x sub n and x sub n minus 1, etc., they are inversely related. A0 multiplies y sub n, and a sub n multiplies y of t, which is y sub 0, okay? So they are in the reverse order. And that makes the differential equation converted into an integral equation format. When we describe everything in the form of block diagrams using integrators, it is going to look in the opposite order, in the reverse order. So the input part, which is B0 x sub n, etc., all those things will look like this. Let me draw it. Now, how can I draw it? First, let's try to look at this input expression. I'm going to draw this as the block diagram using integrators. And every integrator block will convert, let's say, x sub k of t to x sub k minus 1 t. But, sorry, x sub k plus 1 of t, excuse me. So every sub-index of x will be increasing as I use more and more integrators. So I will start from, x of, oops, it's all red, sorry. Let me make it black. X of n going into a system, and then I integrate it. When I integrate it, what am I gonna get? I'm going to get x sub 1. So here it's x sub 1 of, it's not, it's t, of t. And it's not square brackets, it's normal parentheses. Excuse me. So after the integrator, I have x sub 1. And then I integrate it again. And I'm going to have here x sub 2 of t. Okay, after the integral. Now, what is the coefficient of x of t? The coefficient of x of t is bn here, as you see. So I'm going to do it like, I will multiply this one by bn. How about x sub 1? It is the term right before the last term. So the coefficient that multiplies it is b sub n minus 1. B sub n minus 1 is multiplying x sub 1 of t. And this will be in the same order multiplied by b sub n minus 2. It's going to go all the way down to the last integrator, this one. This last integrator will produce x sub n of t, and the one before that was x sub n minus 1 of t. And the coefficients that scale these last signals would be, this one would be b0, this one would be b1. And then I will just accumulate, add them up. Like this. And this is how I achieve or obtain the red encircled input part, which we can also think of it like the moving average part. You remember the ARMA, autoregressive and moving average. This is the moving average part. We are dealing with the input only. We are processing the input. We're not processing the output and regenerating from the output, the autoregressive part. We are not doing it yet. Now we will do the autoregressive part, which is, let me encircle with a green, this portion. That is the autoregressive part. And it's going to process the output. So let me start from the output. Let me say that this is y of t. When I integrate y of t, I will have y sub 1 of t. It looks bad, sorry. Let me try it better, like y sub 1 of t, okay? And when I integrate it again, I'm gonna get y sub 2 of t, etc. And the last integral that I will have will give me y sub n of t. So the one before that was y sub n minus 1 of t. Now, I will feed these outputs, integration outputs, to the left-hand side in a feedback manner. And I will scale them with something. But what is that something? Now notice that I didn't encircle one thing, which is, let me encircle in blue, which is this one. So the green parts are the ones that are having, oh, excuse me, I did it incorrectly. I'm sorry, the green part is expected to be like this. And the blue part is this part only. Because I will isolate it and keep it at the left-hand side of the equation, that is the output, and I will put all the other green encircled, the newly green encircled portion to the right-hand side of the equation. And when I do that, notice that y of n would be equal to, sorry, y of t, why am I saying y of n? Y of t will be equal to this 1 over that, 1 over a sub n times everything that I have encircled in green in a negative coefficient manner. What I mean by the negative is just like we did in the discrete time case, the coefficient that I'm going to write for y sub 1 of t going leftwards will have a coefficient of minus a sub n minus 1. It will be negative, and this will go to the left by multiplying with minus a sub n minus 2. And the one before the last will go to the left by minus a 1. And the last one will go to the left by minus a 0. And then they will accumulate. I will collect them like this. And I will collect it with the input, because the right-hand side red encircled thing is now also contributing to the input, and everything will contribute to y of t, except that it will make actually a sub n times y of t. So I will put a 1 over a sub n here. to normalize for the last thing. This is perhaps way more complicated than the discrete time case, because now we have an awkward 1 over a sub n thing, and everything is in the reverse order, but the negatives are at the right hand side and the positives are at the left hand side of the expression. Now the problem that we have now, the further problem is to minimize the number of integrators, just like the minimization of the number of delay elements. And for that, I will just replace the orders of this and this. There are 2 blocks here. I will just interchange their places. And over there, we will see that from the center block, the input and output relation will look like this. So it's going to look like with a 1 over a sub n from here. And I will have an integrator in the center, and going to the left by minus a sub n minus 1. So as you see, the thing that I'm drawing, this block, essentially resembles this block. Okay, I'm drawing it, I'm copying it to the right hand side. All right. And let's make it longer, like this. Going to the left by minus a n minus 2, accumulating all the way to here, accumulating all the way top, and the last integration. So I have drawn the right hand side block at the left hand side, minus a0, like this. Now the right hand side will continue with the left hand side block, and at the left hand side block, look at what's happening. Follow the yellow cursor. I come from here and I go down, and there's an integration, and I go down and then another integration, and I go down, etc. So this highlighted, yellow highlighted thing will happen, and it's gonna happen now, starting from here, like going down an integration, going down an integration, going down all the way to here with to the last integration. So this is what we are going to have as the left-hand side of the left-hand sided block, the yellow marked thing. But as you see, everything is common here. Like this point is common to this point. Therefore, its first integral, which is here, will be the same as this point. And the second integral or the further integral of that common points, these green points, will also be the same. So why are we doing this? Why are we making these integrals, implementing these integrals? We don't need them. That integration outputs, which will be used for going to the right-hand side from there, like this. These integration outputs, the green, red points, etc., they are all available already at the left-hand side, one left portion of it. So I'm going to erase them. We don't need these. We will share the common integrator from the left-hand side, and we will just use their outputs like this. And these outputs will start from the bottom as B0. This will be B1, and it will continue to B sub n minus 2, B sub n minus 1, and here it's going to be B sub n, and it will be accumulated from the bottom. To produce y of t, where the input was x of t. So what I did was I first interchanged their orders for the first implementation, and I merged all the integrators to a single integral every time it corresponds to the same integration. Quite similar to the trick that we did for the discrete time delay element version. Now here, this portions n and this portions n are the same, and the same problem appears when the right hand side is not n but m. Then what's going to happen? In other words, how can you solve or how can you draw the differential equation, these differential equations block diagrams? And n smaller than m or m smaller than n is also an interesting thing, because that difference in the sizes appear in the differential equation. So you have to just convert everything first to the integral equations. That's a headache. What I mean is this. This is one example. You may want to work on it, but I don't really intend to ask this as an exam question. It would be too difficult. A0 y of t plus a1 y prime of t plus a2 y double prime of t is equal to b0 x of t plus b1 x prime of t. So as you see, the right hand side of the equation does not go until the second derivative. So what's happening here? How are you going to convert everything into an integration form? Let me be honest with you, the way to do this is to integrate both sides of the equation 3 times, because for the left-hand side of the equation, 2 times, you need the first integral and the second integral, because there is a second derivative in the left-hand side. So in order to get rid of all the derivative terms, you have to just integrate all the way to a point that you have no derivatives. In another example, it may be just the opposite. A0 y of t plus a1 y prime of t is equal to b0 x of t plus b1 x prime of t plus b2 x double prime of t. Now this time, the derivatives at the right-hand side of the equation are more. So how many times you have to take the derivative? Again, twice, because you have to get rid of all the derivative terms. And at the left-hand side of the equation, then you come up with a problem, because you're not going to get y of t. You will get only the integrals of y of t, but you will just imagine a y of t which is either to the top or to the bottom of the block diagrams. This is crazy. And if you can work on it, it's going to be really something. It will be a good exercise for you. I would appreciate that. If I want to do this right now, for example, then I may get confused and I may come up with wrong answers. So it will be an excellent analytical exercise for you to try to work on this second example. Some further interesting examples may have, for example, nothing as x of t, but only the derivative, or some of the derivative terms from either side of the equation, from y or from x, may be missing, including x of t and y of t themselves. So you only have the derivative terms of everything. So how are you going to solve those things? But whatever you do, you have to always use integrators. Therefore, first you have to integrate all the way such that you have no derivative term in either side of the equation, and you have to deal with it. And it's difficult. So I'm not going to do it. And again, so I'm not going to ask it. I don't intend to ask a question from these. These are too difficult. Or I wouldn't really say difficult, but confusing. Yeah? I mean, it's not regarding the knowledge and understanding the knowledge, but you get confused while solving these things, which is not an issue for our case. We want to learn something. We want to learn the fundamentals of signal processing. This wouldn't help really. So I'm going to now. We have finished the discussion of linear and time invariant systems. We will continue with a new concept called the frequency analysis of signals. They are also very much strongly related to linear and time invariant systems, but we will see their relation a little bit later. First, we have to express our signal not as a combination or a summation or an integration of impulses. You remember that? Up until now, we were just combining impulses to come up with our signals. The combination could be discrete time combination of separated impulses or a continuous integration of continuous time impulses. But all of them were, so what we did was, let me finally remind you about that. Our idea for this chapter was to write x of n as a linear combination of scaled and shifted impulses. So we were representing our signal using these impulses. We were just scaling them with these and combining them with the summation. Or in continuous time, it was x of t is equal to from minus infinity to infinity x of tau delta t minus tau eta. Again, we were representing in terms of these shifted and scaled impulses and combining them using an integration. So these are representations in terms of impulses. And the impulses indicate time locations. So the impulses are at a certain time on the time axis. So that's why we are also going to call this a time representation. We were combining all individual time elements one by one over the time axis. We were merging those time components and we were getting the time signal. This is a time representation of the signal. Now, in our new chapter, we are going to look at a different representation. We will combine different things which are not located in time, but they are located in frequency. So they will be sinusoids. We will sum up sinusoids at different frequencies. They may be high frequency sinusoids or low frequency sinusoids. We will combine them and they will also make our x of n or x of t, okay? But the additive components, the ingredients, or the Lego components that we have to build our signal will not be impulses. They will not be located in time. They will be located in frequency. They will have a certain frequency. And they will also have a scale, of course. We will have different sinusoids at different frequencies with different scales. We will combine them. We will sum them up. We will integrate them. And we will come up with our signal x of t or x of n. But The problem with that kind of a representation is that the frequencies that we are going to use and the corresponding scales of those sinusoids are not trivial to obtain. Whereas here, they were trivial. Look at this x of k. It is the time sample itself. We already have it. And the position of the impulse is also trivial. It is at k. It was easy. But if you are combining sinusoids, what is the coefficient? It's not going to be x of k, of course. It's going to be something else, a new term. And there will be a formula to get that term, that coefficient. Let's get a sub k, for example, a coefficient for the kth frequency component. And the frequency will be f sub k, which is a frequency corresponding to the kth component. But what is that f sub k? Those will be the issues. We are already 9:40, and we will start a completely new chapter. So I think we may stop at this point until 10 o'clock. At 10 o'clock, we will start with the new chapter. But for the next few seconds, you may try to ask questions, or if you have any questions, you may indicate them. From the things that we have seen already, if you have any questions, you may ask them now. Or if you have any questions regarding the course outline, including the project and things like that, you may also ask it now. And after that, I will stop the recording and I will end the meeting, and we will meet again at 10 o'clock. Until then, do you have any questions now? Okay, there seems to be no question. Okay, then I will stop the recording and I will end the meeting.